And so the next thing to talk about is the model. We haven't talked too much about the model, but as I said earlier, in Model View Controller, the model is where the action is. The interesting state about your application is part of one or more models that it manipulates. And the things your application does are essentially logic in the model, actions that can be performed upon that state. So since we talked earlier about RESTful resources in the context of APIs, and the idea that you should think of your app as a collection of resources and define what operations are being done on those resources, if we apply that thinking to the model aspect of Model View Controller, what do we get? Well, what could you do to a RESTful resource? You could do a lot of things, but the basic actions on it at some level are you can create one, you can read an existing one, you can update one or more state items in an existing one, or you can destroy it. How do you name resources and operations in a web app world? You have the idea of a route, and a RESTful route tries to sort of canonicalize the format of how you name a resource and how you name an operation, which HTTP methods are suitable for which operations, and so on. How does a web app built in Rails inspect or modify a resource? Well, in the Model View Controller design pattern, it's the controller's job to do all the mediation, and it's the view's job to present things to the user, right, broadly defined. So the only remaining thing in Model View Controller is the model's logic and the model state, right? That's where the action is what do you store about the app and what can you do to that stored state? And in the case of Rails, the model is persisted in a database table. So let's talk a little bit more about what that means. So if we go back way, way, way back before we even started talking about web services and just talk about Ruby classes, we had defined our little toy bank account class, and it had a single attribute, which was the balance of the account. It had some basic operations you could do on that stored state, like depositing and withdrawing. And we could create different instances of the account. Every instance of the account has its own copy of the instance variables, like the balance. And every instance can have access to the same methods, like deposit and withdraw, that do something to that state. Right? So that's just sort of basic object-oriented programming. So now if we map this into the database world, let's say that a collection of instances of the same class is a database table. And again, don't worry if you haven't had much SQL. You need about 5 lines of SQL to understand the basic concept here. An instance of the class is going to be one row of that table. The columns of that table are going to correspond to the attributes. So in some sense, like the instance variables of the model. And the model logic, the things that you can do to that resource, are going to be class and instance methods that are defined in the model's class. So in our simple example here, there would probably be a database table with a name like accounts that would correspond to the general resource, the class of a bank account. A column in that table would correspond to the balance of any particular account, and a row in that table would correspond to one instance of the class. So if we had additional attributes of the class, like the account holder's name and other things like that, those would also be columns. So every row in the table essentially has the same set of attributes. And again, does this mean that you can never have any variation? No, but I'm giving you sort of the basic, this is the common case. And the model logic would be where methods like withdraw and deposit are found. Now, remember, these methods, in some sense, the model exists in a little bubble separate from the rest of the world. Just like when we did the tic-tac-toe example game using Sinatra, the logic that plays the game and the rules and who wins and so forth, all of that stuff is encapsulated in basically a model class that knows nothing about the outside world. It has no way of interacting with the user. In Sinatra, the interaction was provided by having methods directly inside of our app.rb that, depending on the incoming route, would call the appropriate method in the model. Here, it's going to be the same thing. So in general, you will not find in the model any code that has anything to do with the user interface or with interacting with the user. The controller's job is to do that. The model's job is to provide a set of operations and some persistent state on which those operations are called. Now, if you have done some SQL, you'll recognize the following. If you haven't, don't worry too much about it. But to map the basic operations of a resource into the structured query language of databases, which is the language long used by relational database systems. In other frameworks that use a backing store, it's pretty common for you to have to essentially construct an SQL statement, and then there's a mechanism that lets you sort of send off that statement to the database and get the result back. Rails doesn't actually work this way for the most part. For the most part, you will work using abstractions that Rails provides for managing the model, and Rails will generate the necessary SQL statements at runtime based on your code. Now, we're going to have a lot to say about why this happens and how it works, but just to sort of get an idea of why this is useful, what are some advantages of doing it this way rather than you constructing your own SQL statements by hand? One of them we'll see is security. There are some very easily avoided pitfalls that can creep in if you're hand constructing your SQL statements. The code generator in Rails that does it avoids most of these pitfalls. But the other reason is that you can actually build up very complicated queries, and Rails will essentially optimize and spit out one big query at the end rather than you sort of having to construct it piece by piece. So there are a number of different advantages, not to mention the fact that in some sense, it, to some extent, insulates the way you think about your model from the details of how that storage happens. There are some places where that abstraction leaks, because all abstractions leak. But for the most part, you can get a surprising amount of the way by really treating your collections of model instances not as database rows, but as objects in their own right. And we'll do a little live demo to show how that works. So in SQL, there are 4 basic operations on a table row. You can create a row in a table. You can read an existing row. You can update one or more columns or attribute values in an existing row, or you can delete that row. Now, of course, before you do that, you have to actually create the table. And every table in SQL has to have a primary key. It's very common for that primary key to just be an integer. And every time you add a new row to the table, it's incremented. So primary keys are never reused, even after you delete the row. So we would create a table with a title column that is a string of up to 255 characters, pretty common. And there's also a rating column, same thing. And now I could create a new row by saying insert into this table, given the column headings of title and rating. And here's a list of 3 things to insert that provide the corresponding values for those. That's the create operation. If I wanted to do a read, I want to inspect the table. I could say, show me, select, all of the columns or all of the rows containing all of the attributes in the movies table where the rating column is equal to the string R. So that's sort of a simple way to do a filtered view. Many other criteria are possible. I can update an existing movie. I can say for any movie that has the title Coco, I should set the rating to PG. Should actually be G, I realized, because it's a G-rated movie. And I can delete something from the table. I can identify the thing to be deleted by its primary key, or I can identify it by some of the other criteria in a where clause, like matching on the value of one or more of the attribute columns. So this is sort of, SQL 101. And if we now map this over into the web app world, each type of model in Rails will have its own database table. How do you know the name of the table? Convention over configuration. Rails will look at the name of the model class that you defined. So in our case, we used movie as an example. We use account as an example. And it will create a database table that pluralizes the word. Why is it plural? Because there's more than one of them. So it makes sense for the database table to be called movies and not movie, because the whole point is you're going to store a bunch of them. And as Michael previously pointed out, Rails does have a nifty little bit of machinery that knows how to pluralize irregular words. That's sort of, who cares cutesyism, but it's good to know. So for example, in English, the plural of person is sometimes said to be people. So if you have a person class, the table will be named people. The plural of sheep is sheep. So if you, for whatever reason, have a model that manipulates a model of sheep, like Dolly, your table will also be named sheep. This is cute. It's not essential, but it's part of convention over configuration. That's how you know the name of the table. All the rows in the table have the same structure. So you're basically deciding what the attributes of a type of model are, right? That's like the instance variables of a class. Once you've decided on what those instance variables are, every instance of that class will have access to the same set of instance variables. And each column of the table stores the value of some attribute of that instance of the model. Each row has to have a unique value for a primary key. And Rails uses the very common convention that it's an integer. It's automatically incremented when you update the table, so you don't have to worry about it or manage it. It's always called ID unless you override it for some reason. And most of the time, when you're doing queries on the database, you don't usually care about the ID because what you're doing is a query that matches on one or more of the other attributes. And the collection of all of the tables taken together, the structure, the relationships among them, things called indices, data structures that can speed up lookups into the table. Collectively, all of that is called the database schema. So the main task that we're going to do next is ask the question, how is a database schema created in Rails when you specify models that you want to have particular attributes? And how do you then manipulate the models in those tables? How do you do the create, read, update, and delete operations on them using the Rails abstractions as opposed to doing it by writing direct SQL statements, which you used to have to do in the bad old days in other frameworks?